So our last lesson in the topic of counting methods is on selections. So selections versus arrangements. Selections differ from arrangements because the order in which the objects are selected doesn't matter. So for example, if I've got 8 people and I'm trying to award first, second and third place, the order that I choose those 3 people is important. Whereas if I just want to choose a group of 3 people from 8 people, it doesn't matter what order I pick them in, I'm going to end up with the same combination of people regardless. So it's about whether or not order is important, and that's what you need to identify from the question. Alright, so if we think first of all about an arrangement, we know about these. So I've got 4 people and I want to know how many different ways can first, second and third place be awarded. Okay, so we've done this before and we're going to have 24 different ways. We could set up a pigeonholing method and we could look at, well, there's 4 people that could come first and then 3 that could come second and then 2 that could come third, and so 4 times 3 times 2 gives me 24 different options. Here are the 24 different options. So first, second and third place could go to the red, blue and yellow people, and then there are 6 different orders in which they could finish first, second and third. Again, the first, second, third could go to the red, green and yellow people, and there are 6 different ways in which they could finish first, second and third. Same for the red, green and blue, and same for the yellow, green and blue. So we end up with 4 times 6, so 24 different arrangements. Okay, so if instead the question isn't about the arrangements, it's just about how we can select 3 people from this group of 4. So here's all the possible arrangements that we had, but we can see that there is lots and lots of repetition if all we're actually interested in is selecting a group of people. So we can see that each of these 4 columns is the same group of people being selected. So there are actually only 4 different selections of 3 people. So there are 24 different ways to arrange 3 of these 4 people, but only 4 different ways to select a group of 3 out of the 4 people. So that means there are 6 times as many arrangements as there are selections. And that's no coincidence. That's because there are 3 factorial, which is 6 different ways to arrange 3 people. So we saw in those columns on the previous slide that for every possible selection, there are 6 different ways that they can be arranged. So that means that the number of arrangements is 6 times too much for the number of selections. So generally, if we have n objects to arrange into r positions, the number of arrangements is npr, okay, which is n factorial over n minus r factorial. Remembering the p stands for permutations or arrangements. If we only wish to select r objects from n objects, then npr gives way too many selections. In fact, it gives r factorial times too many selections. So that means that the number of selections is given by the number of arrangements divided by r factorial. That is npr divided by r factorial. So some new notation. So when we're dealing with selections, the number of ways that r objects can be selected from n objects is found using ncr. And the C stands for combinations. So we're looking at how many combinations can we choose rather than how many ways can we arrange those combinations. But we often read this as n choose r. So for example, as we've been looking at, we had 4 people, we're trying to select a group of 3. We would calculate that as 4c3, which we would think about or read as 4 choose 3. So NCR is the number of arrangements, which is NPR divided by r factorial. And so that can also be written as n factorial over n minus r factorial, which is the number of arrangements, also divided by r factorial. There's not really any need to know this formula. Generally, you'll have your CAS for problems like this, and you can use NCR and just write NCR. So NCR is accessed by pressing menu 5.3, so that is menu probability combinations. All right, let's have a look at some examples. So in how many ways can a hand of 5 cards be dealt from a deck of 52 cards? So the questions aren't going to be specific about this is a selection and this is an arrangement. You're going to need to draw that conclusion yourself, thinking about, is the order important in this problem or isn't it? And in this case, if I'm just interested in getting a hand of 5 cards so that I can play some sort of game, then the order that those cards are dealt doesn't matter. I'm going to pick up my hand of 5 and there'll be the same 5 cards regardless of what order they were dealt in. So order's not important here, which means that it's a selection, and I'm choosing 5 cards from 52 cards. So we're going to have 52 choose 5. That's equivalent to 52 factorial over 47 factorial, which would be the number of arrangements, but also over 5 factorial, which now gives the number of selections. As I said previously, this formula is unnecessary. We can go straight to our CAS from this point, enter in 52 choose 5, and we get 2,598,960 different hands of 5 cards that could be dealt. Okay, example 2. We have a mixed netball team of 7 players needs to be selected from a group of 6 women and 5 men. How many different teams can be selected without restriction? So if there's no restriction on the number of men and women that have to be in the team, we're essentially just choosing 7 players from a group of 11 people. So we want to do 11 choose 7. And using my CAS, 11 choose 7 gives 330 different teams that I could select. Same situation, but this time we want to know how many teams we can select if Sarah, the captain, must be in the team. Okay, so there's one way to choose Sarah, the captain, and, so multiplying, we also wish to choose 6 other players to join her in the team. And again, there's no restriction on whether these have to be men or women. So we've already put Sarah in the team. We have 10 people remaining, from which we need to choose 6. So 1 times 10 choose 6, or just 10 choose 6. Again, going to my CAS, 10 choose 6 gives me 210 different teams that have Sarah in them. Okay, again, same situation. This time we want to know how many different teams can be selected if there must be 4 women and 3 men. Okay, so and is important here. We're going to be multiplying. So we're going to need to choose 4 women from the 6 women. So 6 choose 4. And we also need to choose 3 men from the 5 men. So 5 choose 3. So in total, out of the 11 people, we've chosen 7 people, but we've chosen from more specific groups than that. So again, we're going to go to our CAS. So menu 5, 3, 6, 4 for 6 choose 4, and multiply that by 5, 3. So we get 150 different teams that can be selected with 4 women and 3 men. Okay, part D of the same problem. How many teams can be selected if the team must contain more women than men? Okay, so there are a number of different things that we could have happen here. We've got a team of 7. So we could have 4 women and 3 men. Or we could have 5 women and 2 men, or we could have 6 women and 1 man, or 7 women. So there are 4 different things that we could select. Now again, this is where these addition and multiplication principles are important, and where that very first lesson seems quite mundane and quite routine, but it's important that you stop and think about, is it an and situation or is it an or situation? So we're choosing 4 women and 3 men. So from the 6 women we wish to choose 4, and also from the 5 men we wish to choose 3. So that's the number of ways we could have a team with 4 women and 3 men. Or, so plus, we could have from the 6 women, we could have 5 women, and we could have 2 men. So from the 5 men we could choose 2 of them. Or from the 6 women we want to choose all 6, and from the 5 men we're just going to choose 1. And so whilst theoretically, if the team has to contain more women than men, we possibly could have a team of 7 women, we actually don't have 7 women to choose from. So we've only got 3 different options that we're looking at here: 4 women and 3 men, 5 women and 2 men, 6 women and 1 man. Alright, so let's calculate these. Okay, so 4 women and 3 men, we calculated that on the previous slide. There is 150 different ways for that to happen. 6 choose 5 times 5 choose 2 is 60. and 6 choose 6 times 5 choose 1 is 5. And so we have, 215 different teams that could be selected with more women than men. Alright, the final example we'll look at a sandwich shop, the filling options are cheese, ham, tomato, lettuce, carrot and beetroot. So we have 6 different filling options. How many different sandwiches are possible to make? So we're assuming that a sandwich must contain at least one filling. So that means we could have a sandwich with 1 filling, or a sandwich with 2 fillings, or a sandwich with 3 fillings, or 4 or 5 or 6 fillings. So that means that the number of sandwiches that have just 1 filling, from the 6 available fillings we're choosing 1. Or, so plus, from the 6 available fillings we could choose 2. Or from the 6 available fillings we could choose 3. 6 choose 4, 6 choose 5, 6 choose 6. So we know that this is a selection because the order that the fillings go into the sandwich doesn't matter. It's still going to be the same sandwich. A ham and cheese sandwich is a ham and cheese sandwich, whether we put the ham in and then the cheese, or the cheese in and then the ham. So it's definitely a selection, and we can either choose 1 or 2 or 3 or 4 or 5 or 6 of the 6 available fillings. Okay, so we go to our CAS and work out these combinations. Okay, so 6 choose 1 is 6, and that makes sense. If you think about how many different ways can I choose 1 filling from 6 fillings, well, there are 6 different choices that could be made. 6 choose 2 is 15. 6 choose 3 is 20. 6 choose 4 is also 15. 6 choose 5 is 6, and 6 choose 6 is 1. Again, that makes sense. How many ways can I choose 6 things from 6 things? There's only one way that I can do that. Okay, so adding these up, we've got 50, 62, 63 different sandwiches that could be made. So in summary, the number of ways that R objects can be selected from N objects is found using NCR, which is NPR divided by R factorial, or N factorial over N minus R factorial times R factorial. Again, those formulas don't need to be remembered, just NCR is what's important, and knowing how to calculate NCR with your CAS, that is by pressing menu 5-3. So obviously there are decisions to be made in these questions around, is this a selection or is it an arrangement? And sometimes you'll need to sort of think that through. The other thing to be conscious of is, am I multiplying or adding? Is this an AND situation or an OR situation? That's going to come up quite a bit in these kinds of problems as well.